Whenever you guys are ready, can you explain what you made?
So the goal of this project was to accelerate matrix multiplications using FPGA. And the way that we decided to kind of show the speed up is to render a point cloud. And what you're seeing are pixels, right? And the color of the pixels is representative of the Z dimension of that pixel. So as the pixel goes further back, it becomes less and less visible. You can see on the right side of each box as it rotates backwards, it gets less and less visible. And as it's closer to the viewer, a higher Z coordinate is more bright. And what we're essentially doing is on the startup of our program, we are populating both the HPS memory and the FPGA memory with the same exact data points. And on each loop of the program, what we're doing is we're reading back the return data from the FPGA, plotting it, and then performing the same calculation that the FPGA would have done on the HPS and timing how long it took for the FPGA to signal that it's done with its calculation and how long the HPS takes to perform the same exact calculation.
So yeah, in order to do the matrix multiplication, we developed an optimized matrix multiplication module in Verilog. And the HPS, on the HPS side, it has to do 9 separate multiplications for traditional matrix multiplications, which requires multiple cycles for each multiplication. But our FPGA module only uses four multipliers for performing matrix multiplication and can transform one pixel per cycle. We've been able to develop 15 modules, which allows us to do 15 pixels in 1 clock cycle. And in an ideal sense, we have 15 pixels per clock cycle with a 50 megahertz clocks, which will technically allow us to do 750 million pixel transformations. But from the screen, we can see that we were able to render 4,500 pixels, which takes us 45 microseconds, which equates to about 100 million pixel transformations.
Wow. So as you were saying, since we have 15 modules and each module takes 1 cycle to perform a pixel transformation, taking a 50 megahertz clock, we should be able to create 950 million transformations. But since we are using the ARM to populate the memory, we have to wait for each read and each write. And since there are 3 coordinates, there is 9 cycles where you take 3 cycles to read and 3 cycles to write. Oh, so 7. So 3 cycles to read, 3 cycles to write, and 1 cycle for the calculation. And if you divide 950 by 7, we are getting about 150 million, which is what the clock on the FPGA time shows. So that is then over here we have like the QSys layout with all 15 SRAMs connected. And during our testing, what we realized is the more SRAMs you keep incorporating, the critical path increases, which ends up making the read more than single cycle. So we stopped at 15, and also when we used 15 modules, we were not able to put PIO ports nor switches, and even that broke the read time, the read latency. So in order to show you the X and Y rotation, we compiled with 10 So now we have 2 switches which control so this is along Z, and this is X, and this is the Y. And if you see even the computation time decreased since we are using only 10 modules.
Interesting, yeah.
And because the FPGA parallelly computes all of them, the number of pixels, the increase in number of pixels does not affect the time.
Right.
As long as you don't exhaust all your resources.
That's really impressive. Awesome. Thank you guys. That's really cool.